We are still on thermal expansivity. In this video, we are going to establish a beautiful, elegant connection in thermal physics. The exact mathematical relationship linking linear, superficial, and cubic expansivity. Let's begin with a flat, rectangular metal sheet. At an initial temperature T1, this sheet possesses an initial length L1 and an initial breadth B1. Therefore, its initial surface area, let's call it A1, is simply L1 multiplied by B1. Now imagine we heat this sheet, causing the temperature to rise by an amount. Delta T, what happens? Both dimensions stretch. The length expands to L2 and the breadth expands to B2. Consequently, our new final area, A2, becomes L2 times B2. Keep this setup firmly in your mind as we begin the math. Recall from our very first lesson that the new expanded length L2 equals the original length L1 plus the change in length delta L. And we already know that delta L is defined as alpha times L1 times delta T. Substituting this in gives us L2 equals L1 plus alpha L1 delta T. Look closely at this expression. L1 appears in both terms. If we factor out L1, we arrive at a crucial equation. L2 equals L1 into the bracket 1 plus alpha delta T. By applying the exact same physical logic to the width of the sheet, we can immediately deduce that the final breadth B2 is equal to B1 into the bracket 1 plus alpha delta T. Now, let us find our final total area, a 2, by multiplying our new expressions for L2 and B2 together. This gives us a 2 equals L1 into the bracket 1 plus alpha delta T multiplied by B1 into the bracket 1 plus alpha delta T. Rearranging the terms, we get L1, B1 on the outside into the bracketed product of 1 plus alpha delta T times 1 plus alpha delta T. Let's expand those brackets algebraically. We get a minus 2 equals L1 B1 into the bracket 1 plus 2 alpha delta T plus alpha squared delta T squared. Now pause and look at that last term, alpha squared. In physics, linear expansivity, alpha, is already an incredibly tiny decimal, usually on the order of 10 to the power of -5. When you square a tiny decimal, it becomes so phenomenally microscopic that it becomes insignificant. Therefore, we can safely circle this term and neglect it from our equation. With that term removed, our equation simplifies beautifully to a 2 equals L1 B1 into the bracket 1 plus 2 alpha delta T. Since L1 B1 is simply our original area, a 1, we can write a 2 equals A1 into the bracket 1 plus 2 alpha delta T. Let's save this equation right here. Now for the grand finale, let's bring back our fundamental area expansion formula from the last lesson. A 2 equals A1 into the bracket 1 plus beta delta T. Let's lay it side by side with the equation we just derived. A 2 equals A1 into the bracket 1 plus 2 alpha delta T. Look at them, they are completely identical in structure. By directly comparing these two expressions, we can confidently conclude that beta is equal to 2 times alpha. This explicitly proves that superficial expansivity is exactly twice the value of linear expansivity. Following this exact same geometric proof into 3 dimensions for a solid block, we can seamlessly deduce that cubic expansivity, gamma, is equal to 3 times alpha. An elegant connection, beta is 2 alpha and gamma is 3 alpha. Thank you for watching. And remember to follow the Udimking Education Foundation on our WhatsApp channel and social media platforms for more step-by-step tutorials. See you in the next class.
Udimking Education Foundation. Building confidence, ending examination malpractice for a better tomorrow.
We are building a better tomorrow.
Join us in shaping futures through integrity and education.